All right, it looks like we've got a quorum. Welcome everyone to today's seminar. I'm Craig Keast from MIT Lincoln Laboratory, and I'm actually happy to introduce our speaker, Sam Karlson, who is going to be telling us about the work he and his teammates have been doing on using nitrogen vacancies in diamond for magnetic imaging. Sam, who's originally from Denver, Colorado, is a second lieutenant in the United States Air Force and also a master's student in the Nuclear Science and Engineering Department at MIT. He holds a military fellowship out here at Lincoln Laboratory, where he's working with our Quantum Information and Integrated Nanosystems group. Sam received his BS in physics from the United States Air Force Academy, and he joined the MIT family in the fall of 2022. So I'd like to introduce Sam. I will ask all the folks participating to hold their questions until the end, and we'll have the Q&A session, and you can either raise your hand or write something in the chat, and we'll make sure to answer those questions. So with that intro, Sam, the screen is yours.
Thank you, Craig, for that introduction. As was mentioned, I am a second lieutenant in the United States Air Force, and I'm currently a master's student here at MIT in the Nuclear Science and Engineering Department. And as Craig mentioned, I am specifically working at Lincoln Laboratory in the quantum sensing team with a focus on nitrogen vacancy centers in diamond. And in particular, my project specifically focused on wide field magnetic imaging. There are numerous applications for wide field magnetic imaging in a variety of fields, including biology, geology, and material science. Just a few mentioned that I'm going to mention here include efforts to image neurons and immunomagnetically labeled cells. There are applications for failure analysis for integrated circuits, as well as studying the magnetic properties of superconductivity in detail, looking at vortices and their dynamics. Magnetic imaging can also be used in geophysics to characterize remnant magnetization in geological samples. And there have been demonstrations of magnetic imaging for 2D magnetic materials, looking at magnetic skyrmions. Nitrogen vacancy centers are created by replacing a carbon with a nitrogen atom and removing an adjacent carbon atom in the diamond lattice. These solid-state systems are advantageous over other quantum sensors because they operate at room temperatures and do not require cryocooling. NV centers have stable energy levels suitable for quantum control. The ground state for this system is a spin triplet state. A green laser excites the system. A non-radiative decay pathway preferentially repopulates the MS=0 state, which enables initialization of the quantum state. And one of the advantages of these quantum systems is that measurements are tied to physical constants, which reduces uncertainty and the need for calibrations. In addition, as solid-state sensors, the NV centers are fixed in the lattice, and that is especially important because it enables spatially resolved imaging. And in addition, the fixed orientation of the NV centers in the lattice makes NV diamonds native vector sensors. So by addressing the different orientations in the lattice, you can create the full magnetic vector, recreate, and discover that. The nitrogen vacancy center becomes a magnetic sensor when a resonant microwave field is applied to the system, which transfers population to the MS=1 state. Since more population is in the MS=1 state, fewer optical photons are emitted as they return to the ground state through the non-radiative decay pathway. A static magnetic field causes a Zeeman interaction that splits the degenerate ±1 states and increases magnetic sensitivity. Any change to this external magnetic field will change the resonant condition of the system, so scanning microwave frequencies for this resonance condition can be used to determine changes in the magnetic field. And as I mentioned previously, these measurements are tied to physical constants, so that reduces the uncertainty and makes it a more valuable quantum sensor. More advanced methods of detecting the magnetic field include pulse sequences, and these pulse sequences can improve sensitivity and limit dephasing of the quantum system. My research has specifically involved using nitrogen vacancy centers in diamond and these quantum systems for wide field magnetic imaging. Other quantum imaging techniques do exist that can provide a magnetic image. However, devices like the SQUID, the superconducting quantum interference device, operate at cryogenic temperatures. And so to make magnetic images at room temperatures, they must be separated from the imaged object, which limits their spatial resolution. Other methods like the Hall probe, NV-tip, or raster scanning also can provide an image that has high resolution, but they do not demonstrate time dynamics the way that a wide field imager can. And so as I emphasize at the bottom, only wide field imaging adds spatiotemporal dynamics to traditional magnetic imaging techniques. So the way that the magnetic microscope concept using NV centers in diamond works, we start with our diamond, which has a dense layer of NV centers near the surface where we put our sample of interest. We then shine our laser to optically initialize and read out the quantum state. As you can see here, the laser enters the side of the diamond and totally internally reflects off the top surface. This is advantageous for a number of reasons, including preventing the sample of interest from being damaged by overheating from the laser. We have some imaging optics and a focal plane that senses the fluorescence. Fluorescence from a specific region will pass through the optics and land on the sensor. The fluorescence from each spot on the diamond is mapped onto a pixel. And that happens for each spot and every pixel. And so we place the sample generating a spatially varying magnetic field on top of the diamond. In this case, it's a spiral made of conductive material that we put a current through. The NVs process at different rates based on the magnetic field strength, and the fluorescence is captured on the sensor, enabling us to map out the wide field magnetic image. This is the magnetic image that we created when we applied a 1 milliamp DC current to the spiral structure. And as I mentioned, so some of the benefits of this diamond magnetic microscope is that you can use it for temporal dynamics of a changing magnetic field and also reconstruct the full magnetic vector at each point. Here is a depiction of the magnetic imager setup. The bias magnets split the energy levels of the NV system. The green laser initializes the quantum state. The wires deliver resonant microwaves to the system. The nitrogen vacancy centers emit fluorescence that is captured on a digital focal plane array, which is essentially the camera that we use to detect the magnetic image. And then here on the right is an actual photo of our setup. So we decided to use our magnetic microscope on a through silicon via test chip that we fabricated here at Lincoln Laboratories. This is a visual photo of the chip, and here is a schematic that shows the chip itself. As you can see, the current travels back and forth across the chip in an alternating pattern. And if you look at the bottom image, you'll notice that as it does, it comes in and out of the plane. A change in current creates a magnetic field, leading to the magnetic image that you see here. So this is actually the magnetic image that we were able to take using our magnetic imager. The alternating blue and red stripes reference the direction of the current through the chip, creating positive and negative magnetic field values that correspond to the projection along the NV axis we are measuring on. Here is a video demonstrating the spatial and temporal dynamics of our magnetic imager. We sent a signal current through our silicon via chip that varies temporally as a heartbeat signal. You can see the magnetic field strength change over time and spike with each beat at these two locations on the chip. You can see the initial signal current as well as the corresponding magnetic field in the upper box and the lower box. Since the current is going in opposite directions at those points, they have opposite positive and negative magnetic field values. This diagram shows accomplishments of other quantum sensing methods using nitrogen vacancy centers in diamond. They have primarily been confined to DC and low AC frequencies below about 10 megahertz or in the gigahertz frequency range. As you may notice, there's a fairly large gap between these frequency ranges. Recently, there was a paper that was published demonstrating a method called quantum frequency mixing, which enables us to bridge the gap and detect frequency ranges previously inaccessible by other quantum sensing methods with nitrogen vacancy centers. We applied this quantum frequency mixing method with our magnetic imaging method, and this enabled us to make magnetic images of structures in this previously inaccessible AC frequency range. Here is a schematic diagram of quantum frequency mixing on a magnetic microscope. Quantum frequency mixing is analogous to classical frequency mixing, but it uses the quantum system itself as the mixer, since a classical mixer is too bulky to be applied. Here, the NV centers serve both as the sensors and as the mixer. So as before, a green laser illuminates a region of nitrogen vacancy centers in our diamond. Different regions of the diamond sensor, here they're highlighted by blue and red cartoon spins, respond to spatially varying magnetic fields from the test structure and produce magnetic field-dependent fluorescence, which is imaged onto a sensor array using a set of imaging optics, all as we did with the DC imager. The frequency mixing works by taking a signal field and combining it with a bias field that creates sum and difference frequencies, which allow us to downconvert the resonance frequency, downconvert to the resonance frequency of our NV system. At this resonance frequency, population oscillations occur between the two spin states. The NVs fluoresce such that the photoluminescence oscillates with a frequency proportional to the amplitude of the signal drive field. So by obtaining this frequency, we can determine the strength of the magnetic field. And here, our example test structure generating a spatially varying magnetic field is a Lincoln Laboratory Lisa Ju logo displayed at the sensor plane with a corresponding image of the logo projected at the focal plane. Spatial variations in field amplitude result in variations in the Rabi frequency from pixel to pixel, allowing wide field imaging of AC signal fields at arbitrary signal frequencies. Using this quantum frequency mixing technique, we were able to image the same spiral structure at AC frequencies up to 70 megahertz. So here is a schematic and a photo of the spiral, which we created by depositing conductive materials on a glass microscope slide. Here is an example image of the detected Rabi frequencies of the spiral at a signal frequency of 5 megahertz. At each pixel, we map out the Rabi oscillations of the NV fluorescence and use a fitting function to extract the Rabi frequency, which is proportional to the amplitude of the magnetic field. The detected Rabi frequency is inversely proportional to the signal AC field frequency. So at 50 megahertz signal, the extracted Rabi frequency is slower by a factor of 10 than for our 5 megahertz signal frequency. We plotted the detected Rabi frequencies against the applied signal frequencies for a given pixel, demonstrating this inverse relationship. We naively applied this frequency technique on the TSV circuit chip that we'd previously used for DC imaging, and we quickly noticed that even at low AC input signal frequencies, we could not detect the same magnetic field structure as we could at DC fields, with the structure even less discernible at higher frequencies. After evaluating the device on a network analyzer, we concluded that the chip likely had some capacitive or inductive characteristic preventing us from seeing the structure, likely some capacitive short that caused the input signal to traverse a different path through the TSV chip. In the upper right, we see the absolute value of the magnetic field for a DC signal compared to the detected Rabi frequencies at AC frequencies below it, with the Rabi oscillations for 2 of the pixels for our AC frequencies. And our results here lead us to believe that there may be some application for this magnetic imaging technique for impedance characterizations in circuits. As we noticed that we were able to visually see differences in the DC and the AC where the current might be traveling. So I wanted to just take a moment and thank my MIT and Lincoln Lab advisors. They've done an incredible job in helping me with this, not only just with our specific project and this magnetic imaging, but also just in developing as a scientist and teaching me how to learn and grow in the scientific method. And also just for being incredibly supportive and helpful throughout my entire adventure. So I wanted to give a special thank you and shout out to Paula Capillaro, Danielle Brady, Jennifer Schloss, Polly Cahias, Andrew McCabe, and Matthew Steinecker. They've just been incredibly wonderful to me and helpful through my experience here at grad school. And I wanted to thank everyone else for listening and for hearing this talk.
Thank you, Sam. So we're now open for questions. You can either do that by raising your virtual hand or putting it in the chat. So as people are thinking about it, Sam, I'm going to start with a question. In terms of spatial resolution, what is sort of the spot size that you can image using this technique, or that you've been able to image? A lot of the features that you showed were, reasonably large from a, sort of a microelectronic standpoint, but what kind of spot size can you achieve?
Right. Thanks for that question. So, and just so you know, so like the things that we did image that we have shown here, like the spirals. The spirals are 50 microns in width, and like the actual the width of the conductive material is 50 microns. Here, we initially did a test on a 20 micron structure, and we actually haven't characterized completely the spatial resolution yet. That's actually one of our next steps. This is mostly a proof of principle for the quantum mixing technique on the imager itself. And so that's kind of our next step to determine what the spatial resolution really will be for
Great,
these mixing techniques.
great. Thank you. Again, one question: will the recording be sent to us to watch again? The answer is yes. It will be posted in a week's time or so. So there is another question here from May Kim. Great talk, Sam. I saw that there's heavy damping in the Ravi oscillations and was wondering what that's due to and whether that limits the precision/resolution of your measurement, and how can it be improved?
No, that's a great question. So yeah, the damping is due to the phasing of the quantum system, and that actually was a potential limitation for us in terms of being able to detect the Rabi frequency, especially as we go into higher signal frequencies, right? The dephasing of the system causes the Rabi oscillations to decay faster. And so, especially up to 70, 80 megahertz, we don't even get a full oscillation, and it makes it harder to extract that Rabi frequency. And in terms of, there are a number of things we can do to improve that, right? Removing gradients from the system. We can, play some tricks and games in order to kind of reduce how quickly that gets damped. But ultimately, that is a problem, especially as we get into these higher frequency ranges. Makes it harder to detect that signal.
Again, so a number of questions rolling in here now, Sam. Are there limitations? This is from Emil Patel. Are there limitations today on diamond substrate size and the density of the NV sites?
There are actually, I don't know the specific limitations off the top of my head, but there are limitations to how, because these diamonds are grown. It's a CVD, chemical vapor deposition process, that is how the nitrogen vacancy centers are placed in the diamond, and you can only get to, a specific size. Our diamond is about 4 millimeters by 4 millimeters, and it's about 1 inch in diameter is like the total limitation from what I know.
So next question comes from Colin Dunn. Awesome talk. What are the potential real world applications of your research? I know you actually showed some of those on the first slide, but maybe you want to review those.
Yeah, I'll go back. I did kind of rush through those a little quickly. Um, And so there's a number of applications across a wide variety of fields. The ones that we've primarily been looking at have been for integrated circuits and seeing if we can use them for like fault detection. That's specifically what we've been looking at. Although, as you can see here, there are a number of particularly biological applications and geology. But yeah, we've been looking at, especially for this quantum frequency mixing technique. It's circuits that have signal fields above 10 megahertz, right? I mean, something we were discussing was potentially like RF components that might be useful for seeing the magnetic field for those components.
All right. And the next couple of questions actually come from an anonymous attendee. Again, thank you for a very nice presentation. Very impressive. Just two questions for you. To achieve Rabi oscillations of some fixed frequency, we have high or low signal frequencies to use, as well as magnetic signals correspondingly. What kind of combinations will be preferred? Lower signal frequency or higher signal frequency?
Wait, I'm sorry, could you repeat that one more
Yeah,
time?
that didn't make much sense to me either. So I'll read it again. To achieve Rabi oscillations of some fixed frequency, we have high or low signal frequencies to use, as well as magnetic signals correspondingly. Which kind of combinations will be preferred? Lower signal frequency or higher signal frequency? I,
I'm still not entirely sure I understood that, but I think one thing to emphasize is, in terms of this, at least this mixing method, right? We are try to run through here. Um, we have a signal frequency and a bias frequency, and the combination of those two lead to the resonance frequency of our system. And so obviously we're trying to detect signals that are outside of the range of other quantum sensing techniques. And so, we'd want to use the combination of the signal and bias frequencies that allow us to access those frequencies outside of that accessible range.
and the sort of follow-up question here is, can you, I'm sort of translating here. Can you provide a little bit more details on the spatial temporal dynamics in your measurement technique?
Mhm. Yeah, yeah, so I mean, essentially the way that it works, right, in something like you know, these other scanning methods like an NV-tip, you have to specifically scan across the entire image, uh, measure a single point and then move it and measure another point. And one of the beauties of this wide field imaging technique is that you take the entire image at once, and so it allows you to uh, measure fast enough that you can actually get these temporal dynamics. And as you can see here, right, this signal occurs over the space of about uh, several hundred milliseconds, and you can get a temporal sorry, you can get uh, the time dynamics of about sub-millisecond resolution.
Yeah, thank you. Um, uh, what are the next steps in the project you are hoping to achieve? I think you mentioned some of this. This is principally for for imaging in integrated circuits. Is that what you really hope to be doing?
Right, and also, we want to. So far, we actually are trying to apply the temporal dynamics to the AC frequency range. So far, we've taken images of taken images at these higher AC frequencies, but we are looking to actually make like a magnetic movie of these AC frequency ranges as well.
Mhm. Um, Next question, how can you improve the imaging process with diamond? Because inside the diamond, any light perform multi-reflection by diamond, sir. So I think this is the fact that you have multiple passes, internal reflection through the diamond. How does that sort of boost your I guess your signal? The fact that you're doing total internal
Hmm.
reflection within the diamond. I think that's what they're trying to ask.
Oh, how does it boost the
Yeah.
signal? I do know that there's a way for it to actually increase the contrast by the way that it totally internally reflects and that it's not. I mean, part of it is it's not illuminating the sample itself, right? Which, as I mentioned, also prevents it from overheating, but also allows more light to actually fluoresce back down to the focal plane.
Okay. Um, uh, let's go on to this next one here. How does the measurement of a vector magnetic field work? Um, was it using configurations of the NV diamond centers, and are these known beforehand? I think this is probably reference to the diamond structure, right? Yeah.
Yeah. So the way that it works is the NVs there are four different orientations in the diamond lattice, and so by addressing different orientations, you basically can measure the amplitude of the magnetic field in different orientations, and by using that, you can compile it together to make the full magnetic vector.
Uh, the next question has to do with the temperature of the measurements. What temperature was the spiral conductive material at? And what are the temperature limitations of the device that you're describing?
I mean, the spiral was measured at room temperature. Although that being said, the we used about the laser actually going through the diamond is 1 watt at the diamond, and so there was some additional heating of the spiral based off of that, just kind of it being right next to it. Although realistically, we're hoping to kind of remove that heating element and make it so that it's just measured at room temperature. And sorry, what was that last part? What are the limitations?
Yeah, what are the temperature limitations of the device? I would assume that temperature limitations for the device under test, like
Oh yeah. I mean, I think specifically for the spiral is just like I said, conductive, some metal layers on a glass microscope slide. And so, I mean, it's just as much heat as that can take, which is pretty significant. I mean, I don't think we're gonna fry the glass slide, or unless you evaporate the conductive material off the slide. I think, we're pretty well within the heat limitations.
yeah. I think the question is, I mean, is there a limit to the temperature of the sample that you're trying to measure? I mean, does it have to be within a certain temperature range
Oh,
for that?
no, no.
Okay, okay. Um, Next question from Dane. Great to see the amazing progress on this project. In the TSV image, I was noticing some heterogeneity across the image. Is this due to non-uniform excitation, inhomogeneous magnetic fields, etc.?
I think Dan's referring specifically to like the specific. Uh, um, I think he could either be referring to the bumps or to the.
I again, I don't know if these people can chime in and ask the question themselves, as I look at this image, right, it does vary as you move along the signal path, right? As you move through the via chain, it's much more pronounced in that top row, maybe less so. The intensity is different from row to row, right?
Right. So that in itself could be a number of things. I mean, one is how the TSV chip is actually placed on the diamond. There might be some spots that are a little closer. The beam spot itself, um, it- there has it could be how close the TSV chip is to it. I mean, we've also pushed this TSV chip back and forth on the diamond numerous times, and so the wires themselves might move just a little bit, creating differences in the magnetic field at certain points. So there's a number of reasons why the chip itself might have slightly varying magnetic fields at different spots.
And Dane actually has a follow-up question here. Also, what sensitivity are you getting for the QFM relative to the record values on the chart?
So we haven't characterized the sensitivity yet for the AC signals. It's not going to be as good at DC, particularly mostly because we're limited by the noise in the signal itself. And so our ability to make time average measurements with greater sensitivity is limited by how much noise is in the signal.
Next question, what is the impact of boron and phosphorus doped diamond on NV center properties?
Could you say that one more time?
They're asking the question is, what is the impact of doped diamond, either boron or phosphorus doped diamond on NV center properties?
I actually don't know much about that.
Um, there's a follow-on. Could minute changes in temperature be detected?
Mhm. Yeah, so when we make these measurements, we specifically find the resonance frequency for each signal frequency. And so, if basically when we take our measurement, we make sure that we are on resonance. And so if the temperature changes, we'll be able to detect the change in resonance for the system.
And the question is, how sensitive a temperature change do you think you'd be able to detect?
Um, oh, that's a great, like in terms of, I mean,
Yeah.
that's something I'd probably have to think about. The resonance frequency changes some number like -70 kilohertz per Kelvin or something like that. And so, but I don't know off the top of my head exactly what that is.
So the next question has to do with the depth of field of the imaging system. So you're how deep within an object can you measure the magnetic field, I guess?
That's a great question. So the one of the limitations of this technique is that the standoff distance has to be very close in order for you to be able to sense the magnetic field with high resolution. And so, we're normally, for the spiral images, we're about 60 microns away. If you are much farther, say you're 100 or 200 microns away, you're better off using a different sensing technique like the superconducting quantum interference devices, SQUIDs or something else, because that's just one of the advantages of those systems is that you need to be further away. And so, yeah, for this technique, you want to be as close as you can
Yeah.
to the diamond.
It's a question from Arthur Lobo. Has MIT Lincoln Laboratory developed a low swap NV center diamond magnetometer for magnetic anomaly navigation?
Uh,
Oh,
I am not sure. I'm sure that someone somewhere is working on something like that.
okay. All right. Um, so also, what is the temporal resolution and what controls that? What
Hmm.
controls the temporal resolution? Yeah.
Oh, that's a great question. So for I know it can be the temporal resolution of sub-milliseconds. Um, for I, you know, for ours in particular, it's about, um, what's it? It's on the order of milliseconds, and that kind of depends on the like our the length of our pulse sequence, the camera frame rate, the yeah, how many images we take.
And then this next question, I think you've already answered, but I'll ask it. What are the environmental conditions for your measurements, e.g., vacuum, cooling, cryo, etc.?
Yeah, this is just room temperature. No cryo, no vacuum.
Um, Curious, there appears to
But
be
but one point on that I'd like to add is that you can translate that to a cryo. You could put it in a cryo environment.
there appears to be increased emphasis for high quality visual output of scientific data among various scientific research topics. You mentioned the magnetic movie. What purpose would this serve?
Yeah, that's a great question. I think we talked about circuit and fault detection, right? And so if you're looking for changes in the magnetic field for whatever reason, I think being able to see that within a few milliseconds could be advantageous for circuit fault detection.
Next question, what are the challenges in building arrays, ensembles of these NV diamonds sensor magnetometers?
Could you say that one more time?
The challenges in building arrays of these devices. I think you have a planar surface of these NV centers that you're imaging with a focal plane, right? So
Mhm.
I I guess
But like multiple diamonds in a row, or like an array
I
of
think
multiple diamonds?
that's the way I guess I would interpret it. Arrays of these ensembles. Maybe that's building a very large magnetic imager. So,
Um,
for example, let's say you
yeah.
wanted, magnetic image a body or something like tiling these things together. Maybe that's what
I
they're asking.
mean, well, I think they would get very expensive very quickly. I think one of the problems you'd have is you'd need a lot of lasers to address each one. So you'd need, I mean, because there are limitations to how, as I mentioned, how large you can grow the diamond. And if you just put a bunch of diamonds in a row and you address them all with a bunch of lasers, you'd need a lot of lasers and a lot of laser power, or one giant laser, but that would be very expensive very quickly. So.
Next question: do you have to compensate for the Earth's magnetic field?
Yeah, so in our calibrations, we account for the magnetic field of the Earth.
And the last question, great talk. And again, I agree with that. What are the methods for increasing the contrast in the high frequency range?
Oh, I mean one of the things, there are a number of ways to increase the contrast. Something we've just been, this is something we need to explore on how to do better. But it's, not a problem. I mean, you can put more signal through the device, and obviously that'll lead to a greater contrast. You can increase the amplitude of the microwave fields that you apply to the diamond. Um, you know, there are a number of ways that the contrast can be improved. Reduce, yeah.
One last question snuck in here, and then we'll call it this. How far does the sensor have to be from the magnetic field? And sort of at what distance can you no longer do the imaging? Because you do, in this particular case, show your device right on top of the diamond.
Right.
So
Yeah, no, as close as possible after, if you're even just a couple hundred microns away, you're starting to get to the point where you start to lose your ability to um, make magnetic images with high spatial resolution.
right. Hey, Sam, thanks again for an excellent presentation. And I do want to remind everybody that the next seminar is scheduled for Tuesday, April 9th, and the slot is open. So if you know anybody who might be interested, or if you're interested, please contact Charisse. She just put her email contact in the chat so that we can have a presentation in April. So again, I thank everybody for their time today, and have a good day. Thanks, Sam.
Thanks, Craig.